but it can go as far as you want to take it. So basically,
cool. All right. Thanks, man. All right. Put this here. Okay, can you guys hear me? All right. Well, I'm all right. Okay. So yeah, thanks Sean, and thanks PTM for letting us hang out here. It's a pretty cool space. So yeah, I'm Jason Goodwin, as Sean mentioned. I'm working at Google right now on actually Scala and Akka projects. They're not Google-approved technologies, but I work with a startup that was acquired. So we have to maintain the platform. We do digital ad insertion in linear and VOD. So take video from, like, let's say, ESPN Sports, and then they give us sort of markers in the video that say, hey, you can insert an ad here, and then we take those markers, we go to like Google DoubleClick, and we get ads, and then decision them for each viewer individually, and then we track the viewership back. So we have to scale to very, very large heights to be able to do one-to-one tracking and insertion for every individual user stream. We've done some really, really big work, like up to 1.5 million concurrent live viewers in POCs, and we regularly support a couple 100,000 concurrent users. So we have used Akka to scale our software to really, really large scale, and in doing so, we've also seen AWS and cloud environments and sort of what they really look like when you put a whole bunch of nodes in them and run them for a while. And there are some sort of fallacies, I think, that we all have about computing and networked computing, how it actually works versus sort of our ideal. And I'll get into some of those topics in a little bit, but I did just publish a book recently. And that was a cool experience because I had to ensure like the way that I model Akka and my use of Akka is described fully, and all the sort of small details are clear in my head. I actually learned more writing and introductory work than I ever thought I would. So this talk here is actually sort of very condensed version of that 270-page book to guide you through understanding what Akka is and understanding how you can use it and what sort of things you'll bump into in your first attempts at writing actor code. So yeah, my main objective, I'd like everybody here to walk out understanding what Akka is. If you know what Akka is when you leave here, then I've done a good job, because it's kind of difficult to understand exactly what it is. To put a definition on Akka is not clear immediately, but this presentation will help you understand what it has to offer and what you can use it for. And we'll talk about distributed computing a little bit along the way, because there's some important things that you need to know if you're going to try to use Akka in that context. And I tried to make the presentation both accessible for somebody who has never worked with Akka, as well as people that do have some Akka experience. I still think you'll get something out of this presentation. It's a big subject, and I'll definitely miss a few, of the details that are important or the features that it has to offer. So just to level set, I'm gonna talk about concurrency quickly to help everybody sort of see the traditional problems with writing concurrent applications, and then we'll get into understanding what Akka is by going through the sort of history of the actor model up to today. Today, multi-core computing is growing in importance. We see everything that we use, our phones, computers, they all have multiple cores in them now. My phone has 6 or 8 cores in them. There's new ARM processors for servers that have up to 24 cores. There's a new Xeon processor that has 12 cores. So we're definitely seeing a lot of cores everywhere. CPU speed used to increase every 2.2 years. Moore's law said we get twice the transistors in the processor, and map directly to clock speed, and now we're starting to see that there's problems getting things to go smaller and smaller and smaller. So we're getting more cores, and CPU speed is sort of curving out. And so being able to write concurrent software as users' needs continue to rise every year is important. We need to be able to use the hardware that we have to build correct software still that works, but also build it to be fast on the hardware that we have. It's really easy to screw up concurrent software, though. Most of the applications that are running in production environments that are concurrent, that have concurrency, will have errors in them. Almost certainly, they work by mistake. They'll have race conditions. Nobody will have noticed them in QA because one guy's sitting there pressing the button, walking through the step. But when you throw thousands of users at an application and they're all working with, they're all working on the components at the same time, then problems start to appear. And it's very hard to replicate those problems. It's hard to understand how or why they could be happening. It's even difficult to see that they are occurring. I fixed a race condition the other day. It was in production for a year and a half. And it happens all the time. If I see, these problems come up, you start to look at it, you can't reproduce it, and then you eventually find that there's some weird race condition and it's been there for a long time and the bug has been affecting people and just nobody's noticed. So most concurrent applications work by mistake. It's hard for the developer to see these problems. It's hard for QA to see the problems. The developer looks at the code, thinks, oh, that should work. QA looks at it, going through the flow, it appears to work to them. Even during peer review, right? Like you just don't know. You don't think about those kind of small race conditions. And unfortunately, you have to code for them. So threads are the sort of default model for concurrency that most software is built around. We have many threads that can access one shared resource. So your phone's processors can be accessing some shared resource at the same time. And what we do is we wrap those shared resources with some sort of locking mechanism so that only one thread can get in to access it at once, to do a read, and then later to write back to it. You would acquire a lock. Anybody else that needs access to that resource is going to have to sit and wait in line, basically, for that person to free the lock up again. And most of the problems are around atomic operations. Like if we're just updating something, then we don't really care, right? Like we don't care what order those events occur in. But if we read that data and then do something with it and then write it back, like let's say me and my wife are trying to take out $20 at the same time, there's $25 in the bank account. The two machines read that there's $25 in the bank account, and then they both withdraw $20, and then they both say, okay, now there's only $5 left in the bank account. An extra $20 bill was created there. The system doesn't show that because they both wrote back $5 after they gave the money to us. It looks like there was enough money for both machines. They both took $20. They both write back that there's $5 remaining. The system's not going to even know that that occurred. There's an extra $20 floating out there that the bank doesn't have now. So I'm sure that exact scenario has happened before, and that it took a long time for somebody to realize where thousands and thousands of dollars were going because of some race condition in banking systems. So this is the sort of fundamental problem with concurrent applications, and this is just showing how a write can get lost using incrementing, like something that small and simple as just adding 1 to a value. 2 threads will try to read the value, 2 threads will increment the value, 2 threads will write it back, one of the writes will be lost. It's actually really easy to show in code. If we create this variable I, this was Scala, and then we spawn off 100,000 futures and try to increment that value 100,000 times, you expect the result of this to be 100,000 because we have 100,000 instances of threads like incrementing this one value. But you'll see that even in this like super simple example of going I equals I plus 1, still that one little piece of code, that's not enough to protect against losing values. So you can see the output of that is 94,000 instead of 100,000. So we've lost, 6% of our writes along the way. And it doesn't look like anything's really wrong with that code when you first look at it. It looks like one operation is occurring, so that should be safe, but it's not. So threads, using threads and locking mechanisms, it's really very, very hard to get right. It's an extremely low level abstraction. It's hard to reason about, like locking and how threads are interacting with the lock, and it's just hard to put it in your head. Our brains are not really made for that sort of fine-grained abstraction. And problems won't show up until it's too late. It's really hard to shake it out. Like you can't easily write a unit test or know what unit test to write to find particular race conditions. So threads, I would say, maybe are not the right level of abstraction for humans to be working with concurrency. Another thing to consider when we're talking about Akka, which is event-driven technology, is blocking I/O. So blocking network I/O is a big one. Like if you're reading from a database, these old server technologies, like older Servlet 2.5, for example, in the Java world, it always spawns one thread for every request that comes into a web server. And then if you go talk to a database, that thread just sits around and waits for the response to come back. That's fine. The threads are available for most work at small scale. This is like a fine solution. The threads are available as soon as the request comes in. They pick up the work. They go read data from the database. But when you start to scale to hundreds of thousands of concurrent users, the overhead of managing all of the threads gets higher. The context switching of taking what's in memory, storing it over here so that we can go do other work, and further, because it's like a limited resource. You can only have so many threads. They have a lot of memory overhead. It's not necessarily efficient. So event-driven approaches, which we'll look at with Akka, for example, they tend to scale much better. If you need to do really, really big scale work, event-driven approaches are often better. So just to start to understand what Akka is now, we're going to go back in time and look at the origins of the actor model and what the actor model is. Now we'll start to get sort of a picture, understand the problems that we're looking at, get a picture of what Akka is and how it can help us solve those problems. So back in 1973, Hewitt wrote a paper called A Universal Modular Actor Formalism for Artificial Intelligence. I don't really know. The paper does not really describe, I think, what we're trying to get at it. And the paper itself has a lot of Lewis Carroll quotes, and it's just kind of crazy. It's from a different time when computing was still like a much younger and less sort of developed than it is today. But this is the roots of the actor model implementation of the actor model. He talks about a theoretical model for concurrent computation. So that is just an idea, no implementation. He talks about actors as an abstraction over processes, basically. So these actors are computational entities. They can do stuff, and they hide state away. So there's no sort of things shared accessed by threads at the same time. They're contained within an actor. The state is contained within an actor, and they use messages to talk to each other. So the sort of premise of the paper is that global state is considered harmful. Multiple threads concurrently accessing state is bad. And so by putting the state inside something and not allowing threads to access the state at the same time, we have a potential solution that's a better abstraction. And it's a higher level of abstraction too. So it's not as hard to fit in your head. You can think about simpler, like larger blocks instead of these fine-grained threads. One of the key qualities of the actor model is message passing. So instead of a thread directly accessing some data, actors talk to each other by sending messages. Much like you would send somebody a piece of mail, the message goes into a mailbox, and multiple actors can be sending an actor messages, and those messages just get queued up. They sit on top of one another. That actor, when it's free, it will come take the top message, open it up, read it, and do whatever it's instructed to do, to take whatever response to that message that it has to do. And so one thread is doing that, right? And then when it's done with that message, it will go take the next message, pick it up, and then respond to that message. So right away, I think it's sort of clear how if we only have the actor doing one thing at a time, it gets a lot simpler to think about sort of how things will interact. Like if I have two actors and they're sending messages back and forth to one another, it's a lot easier to reason about put in your head how one actor gets a message, looks at it, looks at its state or whatever, like the state of the situation as it knows it, and responds to that by sending more messages. It's easier to think about than a lock surrounding some sort of shared state and trying to access it with a lock. So if we look at the example of incrementing a number again, if many threads or actors are sending increment messages to an actor, they'll queue up in his mailbox, and he'll have state, so actors can have state inside them because they encapsulate the state. So he'll have a count inside of him, the actor. I use the Alice in Wonderland images to reference the Lewis Carroll references that probably few use, but anyway, so he'll have some state, he'll get these messages, he'll respond to them by incrementing his number is internal state. And we're executing the same thing, right? I equals I plus 1, but because he's only processing one message at a time, now even though it's a concurrent environment, there's multiple people asking to increment the number, we can't really screw it up. There's no race condition. We're not going to overwrite writes because even though it's a concurrent environment, he's only processing one message at a time. So same increment, but now you can't get it wrong because there's only one thread. He's processing one message at a time. So right away we have kind of a solution for that problem, and it doesn't look too complex. It's easy to think about, and it's really hard to get it wrong. So that's kind of one of the fundamental benefits of using the actor model for concurrent applications, is that you can't really get it wrong. If you're sending messages to actors and they're processing them one at a time, then there's only ever one thread that's accessing any state. All state is inside actors, and it's just you can't get it wrong very easily. There's still watchouts and whatnot, but fundamentally it's a much better abstraction for concurrency. So one of the things that we have to do, because Akka is built on top of the JVM, it's a toolkit that you can use with Java or Scala. But because it's not baked into the language, we have to make sure that the messages are immutable. In order for state to truly be stored only within the actors, to have no shared state, messages have to be immutable. So you yourself have to make them immutable. It's easy with Scala, right? Like you make, by default, everything is immutable. You have immutable reference, all of your collections libraries. By default, you're going to use the immutable ones. And so when we send a message from one actor to another, that message can't change. It's like pen on paper. With Java, it's a little bit trickier because Java is not a functional language historically. By default, things are immutable. You have to specify them as immutable collections as well. So you have to be careful with the types that you send around. Guava, for example, Google's Guava has immutable collections. You can make unwritable copies and send them around in messages, but we have to make sure that they don't have any state and that the references can't be changed, so that they're not changing as they're passing hands from actor to actor. So if actors can only communicate through immutable messages, then no actors can access the state of another actor, and there's no state shared between them. Once it's outside of an actor, it's immutable. You can think about it like a message going over the network. Okay? If you send me like if I get a web page and then I change the HTML, it doesn't change it on the server. Once it leaves the server, that's it. It's like out there in the wild. So that's how we want it to look, and you can see, I hope, that then there's no shared state. There's no way for any actor to change anything while somebody else is reading it. So the other quality of the actor model is that the actors themselves are hidden away. The actual, like in Java or Scala, we're talking about an object, an instance of a class. However, you'll never actually see that. You're never going to go new my actor and create an instance. It's abstracted. The creation of the actors is abstracted away, and the actual reference to the actor is also hidden away. So we use these actor refs, like a reference actor ref, that hides away the actual underlying class. And again, the Akka does that to ensure that no state bleeds, so it's harder to screw it up. You can't accidentally have a reference to this other actor, to a child actor. So it takes care of the creation to ensure that the instance of the actor that's underlying is never seen by your code. It's there to protect you. So just to recap kind of step one of the actor model. Shared state is the root of all problems in concurrent systems. That's it. That's the premise of the original actor model paper from Hewitt. And so the actor model attempts to deal with those problems, with the problems especially of concurrent programming with threads, by having actors send and receive immutable messages. They get queued in a mailbox and are only processed one at a time, so that there's no concurrent access to anything, right? An actor is only processing one message at a time. Actors can store state, and they can change their behavior in response to messages. So we can still have state in our applications. Messages are immutable, again, just to ensure that they cannot change. They cannot change while two actors are looking at them. So nothing can change outside of an actor. We can eliminate shared state 100% using this model for building applications. And just model real-world scenarios. I think like a restaurant is a sort of interesting example because we can all relate to it. But we can see how Akka helps us model real situations as we would do in like domain modeling. So wait staff go around, collect orders from people. Those are the messages that they're collecting and sending to the chef. But they don't go and hand them to the chef. They put them in order in the chef's order window, ticket window, which is the chef's mailbox. So the wait staff send messages to the chef, and those messages queue up in the mailbox. The chef takes the orders one at a time, makes the food, prepares it exactly as instructed in the order. So the message contains information that the chef uses to take action, to prepare the food. And then the chef sends the completed food back to the waiter. e.g. puts it on like the wait window or whatever, and the waiters will come up and like process those messages one at a time. So it's easy to reason about, because that level of abstraction over concurrency of the restaurant is sort of relatable for us. It's not difficult for us to think about how these things interact. It's definitely much easier than talking about like threads and locking for concurrent. Yeah.
This comes cost, right? Like I place an order, later on I change my mind.
Yeah, we can't do that. So if you, because the messages are immutable, once you send them, that's it. No shared state. So once it's gone, it's over there.
Okay, so the food is going to be risky. And I mean, this will cost. What I try to say is that.
Yeah, well, usually we're talking about some sort of. If you need to model that, then you certainly can. But the fundamental building blocks are message passing. I mean, you cannot invoke a method and change your mind halfway through, right? Once you call a method, then that's it. You've committed to it. A message is the same way. Instead of invocation of an object invoking logic in another class and them sort of like being tightly coupled, instead of that, I send that other class a message, and it just you can't back out in either case, but.
Like in queue, you can have a priority queue, and you probably can.
You can with the mailboxes as well. Right? Yeah, there's different mailbox implementations, so you can have a priority queue. Right. The priority queues are not particularly efficient though, probably for obvious reasons, because if messages come in, they have to kind of be reordered. So in addition to that, there's also like Akka has a more efficient control message aware mailbox that will let control messages go to the front of the queue. So if you have something important that you want to say to that actor that will change how it responds to those other messages, like, hey, database is down, well, then I can't do all of these things. Then we can stash those messages or whatever. So we can bump those control messages to the front, and that's still very efficient, perfectly efficient, because the queue is still like a normal queue. Yeah.
This example here with the waiter hub would be an actor as well as the customer?
Yeah, the waiter, I mean, I left that piece out because it's sort of leafier abstraction. But yeah, the wait staff would get, I would think of maybe its importance, where you have people coming and like sending messages, how do you want your coffee? And then you collect those orders and send them to the guys making your coffee. And it's all asynchronous, but each person is only sort of posting one message at a time.
Yeah, so it seems to me that this paradigm is better suited for when stuff passes like through some sort of pipeline, right? But your earlier example of APM, how would you scale that using this actor model? Because that would imply that there is just one actor which eventually does the transaction.
Okay, so state and logic go together. This is like, I think we get this wrong a lot in object-oriented programming as well. Martin Fowler calls this a mnemic domain and model name pattern, where you have some data in an object and then like logic somewhere else. It should go together. So if I was to model a banking scenario, I would model the bank account as an actor. The bank account is an actor. And the atomic operation that we want to model, our message, is like withdraw $20. The bank account knows how much money it has. It processes messages one at a time. It sees my request and my wife's request, but they go in the mailbox. It takes one, goes, okay, I have $25. Can this person withdraw $25? Yes, they can. Send back, an okay, withdraw $20 from the machine, and it will pull $20 out, and I'll decrement my internal state. The next message, I pick that up and process it. My wife now, her request comes, and it says withdraw $20. I check my state. It's only at $5 now, so I can't do it. I send back an error instead. I don't decrement the balance. Yeah, thank you. Does that make sense? So I'll get to this a little bit more too, because it's a different paradigm. Like, to think about how to model things is different, but primarily you want to think about state logic and those operations. You want to tell an actor what to do, not like ask it for things, right? We're not going to ask the actor how much money do you have, and then say, okay, can you go minus 20 now, because that's like what kind of an actor is that? It's just holding data for somebody else to do stuff on. You want to put the logic and the data together.
But on the ordering of the messages,
ordering of the messages are guaranteed from one actor to another. So if I send you 3 messages, you will receive them in the order that I send them to you. But beyond that, it's non-deterministic. It's a concurrent environment, so there's like looser guarantees about the ordering of messages. Yeah, it's typically not a problem. I haven't seen many cases where I've had to really like think too hard about the ordering of messages. Primarily because you'll tend to like kick up things as temporary sort of pieces for the life cycle of a request. I'll get more to that in like the sort of effective use area, because these are really great and very important questions. If you want to get into using Akka, understanding the heuristics of designing with actors is important. It's very easy to get wrong. So these are definitely like the right questions to ask. Yeah.
Just a follow-up to the last question. So the diagram shows the restaurant model.
Yeah.
What if I want to have 2 chefs?
Yeah, sure. So you would have one mailbox,
Right. And then we'll pull.
and 2 actors pulling from it.
Okay.
And so that would be a router in Akka. So Akka does have mechanisms for placing pools of workers and you know, efficiently distributing the messages to them as they have the ability to take work, for example. And we'll talk about location transparency later, where those actors could be in different machines as well. So we could have a cluster of servers, and we're sending a message, and they're getting distributed to, like, you know, multiple computers or VMs in the cloud doing work. And it's no different in the code, but yeah. So it's a router, a grouper, router pool. So you were to look in the box. Sorry?
Would they share the state?
They do not share state. They would each process. So I mean, they don't need to, right? Like, if you have 2 chefs working at a table, I'm like, okay, what am I gonna make? I'll make it, and then I'll send that to the waiter. The other guy, it doesn't matter what the other guy's doing. So the only thing they'll share is the mailbox. They'll pull messages from the mailbox.
Yeah, but to build on your account balance example, you wouldn't have 2 account chefs.
No, certainly not. Yeah, because you only have the data in one place. You'd have a checkings account and you'd have a savings account, but because that data, that state, it needs to be strongly consistent. You can't replicate it or anything, right? There's only one account balance, so that can only be in one place. Yep.
What if the result of the process depends on the result of each actor?
So you're saying somebody comes and they want to see their bank account information, and we need to show them their savings, checkings, and credit card. How do we get the data together? Okay, sure.
Say that we have an order of the meal, and it's separated to have it ring and have something.
Yeah. So how do you coordinate work across multiple actors?
Yes. So one chef takes the ring and another takes the meal. So they join together and send back the order.
Yeah. Yes. I'm going to cover that. When I talk about extra and cameo pattern, I will talk about how to coordinate work amongst actors and I'll try to remember to use that example of, like, what if we have, you know, one person producing vegetables, one person cooking the meat, or something like that. How do we put it back together? That was what you're asking, right?
Yeah.
Because I will get to that very soon. Okay. Okay. So I just wanted to show you what the code looks like quickly. Might be kind of hard to read, but so the first thing is an immutable message. I show a little bit of Java here. The second one is Scala, obviously, because it's more succinct. The first is an immutable message. Int is immutable, right? Strings are immutable. So in this case, we don't need to worry about the type too much, but. So we have an int and a constructor to set that as we final. So we have an immutable reference and immutable type. And then Scala is just straight up simpler case class for an immutable message. For an actor, we would look at something like this. So an actor has state. So we have the value. And then it has a receive block that describes how to respond to the receipt of different messages. So in this case, we see blocked partial functions. So we use pattern matching in Scala. We say, okay, if the message is a get an increment message, extract the value of an increment by, then value equals increment by. It's pretty straightforward. That's the anatomy of an actor. The simplest actor that you can make, more or less. And then also, you can send messages back to other actors. We can send messages to the sender. So here we've said, okay, the guy who sent us a message, we will send him the value after incrementing. I think it actually should be the other way around. It should give the, like, for an atomic integer, but oh, anyways. Java, very smart. So Java 8 has lambdas. Woo! It's awesome. We're doing async work. It's like critical. And Akka has a newer API for using with Java 8. It lets you build a partial function. You can't do that kind of pattern matching naturally in Java, but there's this builder that lets you describe the cases in Java using lambdas. So we have the type, get an increment for this match. If this message is get an increment, then we have a lambda here, which we know is this type. So, so same thing. We just, you know, change our internal state by adding the value and then send the message back. So it's not too bad actually. Like for Java using the lambdas, it's fairly succinct. Scala is certainly a nicer pair because it has partial functions in the core written language. It has pattern matching and the extracting from case classes and whatnot. So it's very succinct and clear, I think, with Scala, sort of how it's put together. And then we talked about how we never see the instance of the actor itself, the actual running object. So I'll just show the creation, the instantiation of an actor and getting the actor ref. So an actor system contains all your actors and whatnot. When we have a reference to an actor system, we call actor of, and then we pass the information needed, the type and all of the arguments for the constructor through this like props object. So then Akka takes that and it, like using reflection or whatnot, builds the instance of the actor for us. And we never see it. Then we just get back this ref that lets us send messages to the mailbox. So we can take that ref and this is read tell. Actually ref tell, the exclamation mark, it means tell, fire and forget. So send it a message. And then the get and increment that we talked about. So yeah, you'll see that here too. Sorry, I didn't mention that, but Scala, because we can use whatever character we want. You could like make a machine gun for your class name or whatever. Akka uses tell, the exclamation mark. That's a throwback to Erlang, which I'll cover in a little bit. So that's the basics of what an actor is and how they work. But there's a lot more. Akka is not simply an actor model implementation. So we're going to keep going through the history a little bit of the actor model to understand where it comes from, where Akka comes from, and its qualities and why they're there. So in the 90s, Ericsson, maybe 80s, I think Erlang started being built. Erlang is a functional dynamic programming language that was used by Ericsson to build embedded telco systems. So they built like telephone switches and using Erlang. And Erlang had an actor model implementation that's a little bit further than what was described in the original paper. It adds supervision, and we'll get to why that's important in a little bit. But let's talk about their uptime, because this is amazing. They produced this switch, I think in 1998, AXD301, which achieved 9 nines of availability, which is 5 seconds of downtime in 100 years. Basically, like, as long as the application could be running, it was up. That's insane, right? We don't even talk about nines to that degree, you know, like 3 or 4 nines. We're talking about for like uptime outside of maintenance windows. So Joe Armstrong from Ericsson was asked how they achieved these staggering results. And his answer was no shared state, which we covered, plus a sophisticated error recovery model. Okay, so back to the restaurant. Our chef, every time he finishes a plate, he takes a drink. Okay? So eventually he gets into a worse and worse state, right? We've gone through, he's still making plates, but like there's some kind of problem with this process if he's taking a drink every time. We don't notice it when we're testing, but you know, after an entire night, he's taking a drink after every plate, he gets drunk. Right? Eventually he's like laid on the ground or generally screwing things up, and the supervisor notices, oh, he's like made a mistake, he's a mess. So that escalates, right? The supervisor, his manager, sees him making a mess of the plates or harassing the customers or whatever exception he's throwing. And the supervisor decides to take action in response to that exception. So in this case, he's going to send him home and bring on somebody else. He's going to call his replacement in and send that guy home because he's wasted. Okay, that's like restarting. You kill the old one, you make a new one. This is the and the thing that fails is not what's responding to the failure. So these are the kind of qualities. The manager replaces the chef with the sober one. The manager makes the decision, and then the new chef continues to process the orders. So you can see, like, you could run a restaurant for a long time. If that's how they work, and they're taking a drink after every meal they prepare, you need to have you need to be able to bring new guys in to replace them. They'll eventually get into a bad state if that's how you're operating. But that's fine. You can just keep doing that. If they get into a bad state, your restaurant's going to stay up as long as you can keep replacing the actors. So actors exist in hierarchies then. In order to have a supervisor, there has to be like the supervisee. And this is modeled like a folder structure. So at the root, there's what's called the guardian actor that's created sort of from the application starting. They're by default going to be supervised by this guardian actor who has some default supervision strategies. So if you throw an exception, I'm going to restart you. If you throw an error, I'm going to shut down the actor system. We're going to just crash the application. If I get an out of memory error, I'm not going to try to deal with it, right? But otherwise, like, my default strategy is going to be to restart you. So when an actor creates a child, it will supervise that actor by default. So as we create more actors, they'll be supervising the actors underneath them. Yeah, so we discussed this a little bit. When an exception occurs, when the chef's exception occurs, the supervisor, the guy that's above him in the tree, right? We have the chef and the restaurant manager. He's going to see that exception and respond to it. So the restaurant manager can have these different responses to different errors, like drunk chef error is different than restaurant on fire error. Right? We're going to take different responses to those scenarios, and we can also escalate them. So there might be the owner of the restaurant. If the restaurant's on fire, then the manager might not know what to do with it. He may not have the right sort of context or whatnot to understand what to do with it. So the restaurant manager might call the owner and go, hey, it's on fire, what do we do? And they'll say, the owner will say, well, get everybody out, like, get everybody to the restaurant right away. So these like hierarchies will let you sort of have actors understand different things about how to respond in the error scenarios, for example. But every actor is supervised, and this is the sophisticated error. So the response to failure is done outside the thing that fails. That's kind of the key quality here. By moving it out and having some like sane strategies for dealing with those problems, we can generally assume that things will go bad eventually in unexpected ways. And then we can just like recreate those pieces of the Ericsson. So we don't need to write code for every single error scenario. If something goes wrong, we'll just assume the worst, shut it down, and make a new whatever it is that we're talking about. That piece of the application, we can just recreate it. And that way we don't need to code for every last scenario, every last error case. By removing the response to failure from the thing that fails, we can be pessimistic and just recreate it if something goes wrong. So it's like the Akka blog, if you look at it, it'll say, like their slogan is "Let it crash," and that sort of pessimistic attitude gives you like fault tolerance. You know, your pager won't be going off. You'll get nice sleep at night. Hopefully, right? If it works, if it doesn't crash entirely, and you're able to like keep sending them that drunk chef, then you're gonna be able to keep things up. So yeah, just to recap the whole supervision thing, the AXT 301 achieved ridiculous uptime. 5 seconds of downtime in 100 years if the application could be running. It did this by using the actor model to eliminate shared state, and also contributed a sophisticated error recovery model, the supervision, so that we can be pessimistic, let it crash, restart. That's how they did it with the AXT 301. That's how, you know, we're doing it today with Akka. Actors exist in hierarchies, where parents supervise their children. We can be pessimistic and expect things to fail in unexpected ways, and we want to remove the response to failure from the thing that fails. That's the qualities that Erlang contributed to the actor model. I'll just quickly show you in code. So we'll look at an actor to demonstrate supervision. Our actor has some state, which I didn't write an implementation for. It has the behavior, the response to messages. Again, not been implemented, but you would fill it in, obviously. However, now all we have to do in the actor, because every actor can supervise its children, we just override a supervision strategy and define whatever response we want here. There's a few responses that we can take. We can choose to restart the actor, recreate it, resume it. If it's like a non-critical error, maybe we just want it to continue to process the next message. We don't need to recreate the actor. Stop, that's like an Erlang throwback. You can watch an actor's life cycle. You can see if it get a notification if it dies. So stop is there if somebody else is gonna, kind of deal with that terminated message. Because you'll stop them and then a response will happen. You don't usually use that one. It's just the default if something crashes when it's instantiating, like if the actor's constructor fails. And escalate means send it up to my manager. All right, so now we're going to look at Akka's contributions to the actor model. If we looked at the history, yeah.
So quick question is, what happens when an actor dies and say, I agree, the supervisor basically responds and the actor, like, what happens to the message box of this actor?
Yeah, so the current message is dropped. Again, we assume the worst, right? We're pessimistic. So if that message is causing the problem, then the default, this is a default. You can make it, we have to do whatever we want, but by default, we drop the current message, assuming that it's somehow problematic or caused the problem, and we restart the actor, meaning that we assume that the actor is in a bad state, and the actor's state caused the problem. So we can, retry the message, but by default, we'll drop the current message and then continue to process messages from the mailbox. So the mailbox stays there if we restart the actor.
What happens if the supervisor dies?
If the supervisor dies, the children are shut down and fall. Yeah. Yeah, there's hooks in the actors for their life cycle as well, so you can during restart, pre-restart, post-restart, pre-stop, we can write different behaviors. and have them occur in like only circumstances, for example, like only stopping, not restarting. There's hooks there to let you sort of like change the behavior of the life cycle of the actor as needed. Like you might want to log, right? For sure you want to log if actors are restarting, so you would get into the hooks and change that behavior. So, okay, cool. Any other questions on the sort of supervision piece? Yeah?
The message drops, how would this set right now?
So in a concurrent application, you again, like, you want to be pessimistic. So you would, if it's important that the sender receives a response, you would be bound by time. Okay? So if you don't receive a response in time, you'd want to retry. And again, we'll talk about location transparency in a little bit. That actually could be local or remote. So if the actor is on another machine and the message is going over the network, there's a lot of things that can go wrong with the message along the way. Okay. So yeah, Akka is relatively new. The first release was sent out 0.5, I think, in 2010. Akka is an actor model implementation. I'll give a better definition later, but for the JVM, it's heavily inspired by Erlang's implementation. If you're ever thinking, why is it like that? Why is the default like that? Why is it called tell? Why are we using the exclamation mark? You can probably look at Erlang, just go dig in, and you'll very likely see that these sort of actor model pieces are very much modeled after Erlang's implementation. So Scala was starting to get some attention around then for use in server applications. Like Twitter started using Scala in 2009, which is a big sort of piece of Scala's history. They have some important contributions to it. And so Jonas, yeah, he started working on Akka. And so an actor system in Akka contains everything. It's a heavyweight sort of abstraction. You usually want one for your application. You can have multiple actor systems, but you typically would only have one. That's where everything resides in Akka, inside the actor system. So that you'll see very often, if I'm showing you code examples, like creating an actor, we need to reference to an actor system. If we're going to use a scheduler, the scheduler has to exist inside an actor system. So actor system is a critical container for all of this stuff. It also has the scheduler / dispatcher, like they're based on executors, Java's executors, so they'll abstract away thread pools and whatnot. That's what makes the actors really tick. There needs to be like the dispatcher. This is kind of the interesting piece of Akka's contribution. Although location transparency was discussed in the actor model implementations before it, Akka has really taken location transparency to a new kind of level. So that location transparency says it doesn't matter where an actor is. We have a reference to it. It can be located on another machine. It can be located locally on the same, like in the same application instance. So it doesn't matter. The code doesn't change. If we send a message to an actor, it could be somewhere else, and Akka will abstract that away from us. And that's pretty cool, right? I can have an application to run, and then I change the configuration, and now it's like in the cloud and 5 different machines or 500 different machines. So each actor has this URI, the protocol, just like this is like a HTTP URI, right? Obviously a different protocol, Akka TCP. The actor system. So we mentioned that actor system is what it runs in, because you can have multiple on a host, for example. We need to describe that. The host and port, because we're using TCP to talk. And then the path of the user, which we looked at earlier. So the guardian, the parent, and the child actor, for example, in this case. And so the key thing, again, if I go local actor tell, send it a message. Or remote actor tell, send a message. It doesn't look any different in the code. There's nothing there to say that guy's remote. It's configuration, it's runtime configuration even. So you can have like the same code run in different ways just by describing the location of the actors differently. So yeah, it gives us flexibility in how we deploy. It can be a runtime decision, as I mentioned. But there's some problems, like, again, the fallacies of distributed computing. Like, things go wrong when you send stuff over the network. So using remoting, like peer-to-peer communication, might not be the right solution for all applications. So Akka has given us a pretty amazing tool. I think that this is actually like amazing. It's really, really amazing. Akka has a newer module called Cluster. Came out, I think, in Akka 2.3. And 2.0, I don't know. Recently, in the last couple years, I think Cluster was introduced. So this allows us to build distributed actor systems. We can build an application with actors across a bunch of servers, and we can add or remove nodes from our cluster dynamically. So if we have a bunch of, if we know, like, we did some marketing, and we're going to get a whole bunch of traffic on our application, you don't have to like shut down and reconfigure everybody so they know how to talk to all the other nodes or whatnot. You can just add more nodes to the cluster, and it will grow dynamically live. It will tell all of the other nodes about the changes, and it will tell the clients about the changes in the application as well. If you're familiar with Cassandra, for example, or any of the Dynamo-style DBs, it's very similar implementation. It's very much Dynamo-inspired, Akka's cluster mechanics. However, we can use it to build our own applications. That's the coolest part. Like, that's amazing. It's so awesome that you can sit down and with a couple hundred lines of code, you can be building your application in a giant cluster and talking to that cluster. Like, literally a couple hundred lines of code. You don't have to worry about all of the gossip protocol implementations. And of course, so that's better than the peer-to-peer communication because it's highly available. If a node dies, then I don't have to worry about like writing all this behavior to talk to other nodes in the cluster. Cluster abstracts away more and more for us to let us only deal with the code of, hey, I need to send that guy an actor. Or I need to send that actor a message, rather. So Cluster is a Dynamo-like implementation. If you're curious about how this works, I would read the Amazon Dynamo paper. It's not too difficult to understand. You can also look at Cassandra because Cassandra is a Dynamo-like database that implements gossip protocol, very similar. The way that Akka Cluster works and Cassandra works are similar. So reading or watching presentations about Cassandra will help you understand how the cluster fits together and grows and shrinks. Yep.
Cluster module allow for rolling updates.
For rolling updates? In terms of your application?
Yeah.
So your messages, so it's a good question. Are you familiar with protocol buffers? Google's protocol buffers? So if you have a message that changes and you're serializing it and sending it to a different version of the application, when it deserializes the message, if it's not the same, it's gonna like crash, right? So you need to use for network communication protocol allows multi-message to be used. And Google has this tool called protocol buffers, which will generate your Java code for you. There's Scala one, so I'll use it at Google for sending messages between our machines because we do update them and they're all talking to the network. So protocol buffers is like is an alternative to Java serialization, for example, that lets you have version messages that will like be compatible across versions. So you need to ensure that when the actors are talking to each other, that they're able to communicate. In that regard, if you're using protocol buffers, for example, you have to dig into the serialization that Akka uses a little bit, but you just need to ensure that the messages are able to like be deserialized by the parties that will consume them. But yeah, it's possible to do for sure. Yeah, I gave a presentation at Netflix recently on using Actor Cluster because they were having problems with like with upgrading this component of Spinnaker. It's like a DevOps kind of tool for build pipelines. And that was what they were looking for, was to be able to like add new versions and then shut down the old versions without interrupting service, to do it quickly and easily. And I'll tell you a couple more items in Akka that like will help you manage the kind of changing of code over time. But yeah, it's possible. So just kind of at the root, we have like a bunch of nodes. A new node comes in. You're trying to add a new node. You will announce to the coordinator, "Hey, I'm trying to join the cluster," and then this guy will tell another node, and they'll gossip through the cluster. Like it's called gossip protocol. They'll tell each other through the cluster that there's changes to the state occurring until they reach consensus about the cluster, and then boom, it's suddenly bigger. And a node leaving the cluster gracefully will also announce, "Hey, I'm leaving the cluster." If a node crashes, Akka does like a health check. Each node checks a couple nodes beside it, and they'll notice that somebody's unavailable, and so they will say, "Hey, don't let anybody join or leave the cluster because we have this like issue right now." And then they'll try to wait for it to come back into the cluster, for example. So it has these tools for sort of managing these normal situations, and it totally abstracts it away from you. All you have to do is start the servers, and they'll talk to each other, and your application will get the the updates it needs to the state of the cluster. So yeah, gossip protocol is what's used. Cassandra, Dynamo, you'll see it if you look around. So just talking about, for example, how to manage multiple versions in a cluster, or if you have a state, for example, that you need to like migrate from an old version to a new version. Let's say you have a job queue in an actor. There's only one job queue, and you're trying to like roll out a new version of the application. You need that job queue to move to the new version of the application. That sounds kind of like a challenging thing to do, right? How do we get that state that's in that application over here? Well, we can put it in a database, like a distributed database. That's certainly feasible, but actors happen to be like a nice natural way to keep state for running applications. Well, it's faster if it's in memory and whatnot. So we can do that. We can use some kind of persistence mechanism to give durability to an actor's state. So after it processes a message and applies it safely to itself, it will say, "Hey, this update occurred," and it will keep some sort of log somewhere. And then if it crashes or whatever, if the application crashes, when you restart it, it's able to read back out and reapply the state, and keep snapshots as well to keep that like from becoming a huge list of things that need to apply. But by using it, it's called Akka persistence, the piece that persists it. And then like there's like a singleton module that will sort of take care of migrating an actor through. So there's some really cool tools in Akka cluster, around the Akka cluster modules, that let you build like really awesome clustered networked applications. So I think like this, just to say, hey, what is Akka? I think that these are two specific definitions. Like it's not just an Akka model implementation. It's not a concurrency framework. It's not really a framework at all because it has all this other stuff like cluster and persistence. It's not a framework per se. It's not cluster implementation because we're not necessarily talking about like distribution. We could be talking about distribution across cores. So it's concurrency and. So my definition, I don't know, this makes sense to me. Akka is a toolkit for building fault tolerant. We talked about the sophisticated error recovery model. Distributed systems on the JVM. And I put concurrent and in like small letters here because I think that we can talk about distribution as the same thing as concurrency. Like if we have actors in different cores, that's kind of the same thing as having them across the network. It's still somewhere else. So multi-core we can talk about as a distribution problem. With location transparency, it doesn't matter if it's another core or another machine. So I think like this is what I think Akka is. A lot of people talk about reactive. Have you guys heard that term? the reactive manifesto, reactive applications. Even in JavaScript today, you hear like React.js, and this stuff is blowing up. On the server side, we talk a lot about reactive today and things being like asynchronous, event-driven. It's like all the rage, web scale. So the reactive manifesto kind of came from TypeSafe and a few key members. The idea is that there's these sort of 4 qualities that we want in our applications today. If we have users interacting with our applications, they should be responsive, right? We don't want users to wait around. We don't want them to wait because they will go somewhere else. So our system should respond in a timely manner, if at all possible. It should maintain responsiveness. It should always be responsive. We put the user's experience first. And there's a really amazing study that Google and Yahoo, Microsoft, I don't know, Google, somebody else did about like users' expectations several years ago. They found that they had to like cancel this whole study because they found that introducing time, like delay into search, call it anything past 2 seconds, the user would like be apt to navigate away. And they canceled it because it was costing too much money. Like people were, what is this? Like it was statistically like very irrelevant. That's a good thing to read, and I'm sure it's even more insane today. Like probably if things take more than a second, people are I don't even realize that they're like frustrated, but it changes their behavior. So we need to keep things responsive, or we'll lose our users, we'll lose our revenue. Resilient. The system should stay up. I mean, it's not acceptable if I need to access the service, it's not available. You know, maintenance window, whatever. Or it's crashed because of whatever XYZ reason. So we need to safeguard our applications against all the things that could go wrong, either in the code, like things blowing up, getting a bad state, or in the infrastructure, nodes or availability zones dropping, servers being unavailable. We need, if we have a bunch of people that come onto the application because it's suddenly popular, reached the top of Hacker News or whatever, and there's hundreds of thousands of people piling on, we need our system to be elastic as well. It needs to stay responsive under varying workloads. So we need to be able to add and remove nodes from a cluster, for example, in order to accommodate in an emergency extra traffic and have our application still be responsive. And message-driven, this used to say, I can't remember, it used to say something else. It changed the reactive manifesto to say message-driven. I think it said event-driven before, but the message passing thing is a good paradigm. So they just say rely on asynchronous message passing to establish a boundary between components that ensures loose coupling, isolation, location transparency, and provides the means to delegate the errors as messages. Really what that's saying is everything that we've talked about already, right? The boundary between components, like keep state over there, ensures loose coupling. If that thing fails, it's not going to affect this thing over here. All of these sort of principles really are covered in the Akka model. So the Akka model is asynchronous and event-driven because the actors respond to messages. They don't like wait around for anything. So I'm not going to take too much more time. I do want to plow through a few more slides on effective use of Akka. And I have some stuff I'm going to cut out at the end about distributed computing. I won't cover it because we're going to run a little bit too long. But so I just want to make sure that I get this piece out though. So you can use actors like OOFP. Or I'm going to talk about effective use of Akka. The paradigm heuristics that you really want to ensure you have and understand when you're modeling with actors. So it's a possibility to do things with actors like we would with objects. Okay? We can ask them for data and do things with the data that they have and interact with things in that kind of way that we do objects. And it's probably gonna, you're gonna have the thought quite often, oh, I would design it like this because this is what I know. This is how I've always worked. It's kind of like, object-oriented and functional programming. They can be done in similar ways as well, but there are different approaches, different heuristics. The problem with using Akka like actors, like regular objects, you lose type safety right away. So the messages that actors send, this is called the ask pattern. Okay, so this says I'm going to give the actor a message. I'm going to get back a message in a response asynchronously. So it's a future. The question mark, that's ask. So that looks like invoking a method, right? I'm going to pass it something and I'm going to get a response. But we lose type safety because the messages are untyped. The actors do pattern matching to sort of type things again inside the actor code. So this has problems, and it's not better than using features. Features are typed. If you're just trying to get asynchronous, then you can use features. You don't need to use actors. So if you have state, though, because we talked about this a lot, right? I hope I've hammered this in. If you have state, then actors are a good fit. State and distribution. If you have concurrent environment or an environment that's spreading multiple machines, and you have state, actors are a good fit. So you don't want to have multiple threads accessing things in your actors. It's certainly possible to do that. You can have futures in your actors, right? Here's an example. We have this like HTTP request, and then when it's done, we're going to update the state in the actor and send her a response. Okay. And if you've worked with Scala, it's a Scala meetup. I'm assuming that there's some like familiarity. So we have a callback here that executes when that feature is complete. This is really bad. We lose all the benefit of using Akka immediately because we're extracting the state in the actor from another thread. So we've lost it already. Like all the benefit is gone. So there's a different heuristic we have to take when working with actors. We don't want to necessarily mix in asynchronous stuff. We want to use actors. We want to use actors as the primitive. So a bit better, like you can get away with using async libs instead of in the callback here. Like what we're going to do is instead of acting on the state, we're going to send ourselves a message. So pipe says, okay, take the result of this future and send it to this actor. So that's the sort of safe way to flatten it back out to get if you're working with asynchronous code. You don't want to act on stuff within the callbacks, within the asynchronous closure. You want to send messages from there and then have the actors respond to things. So if you see like async code inside your actors, send the actors messages from those contexts. But like at its best, we're not going to ask our actors for stuff. We're going to tell them to do things. And this is like the key heuristic that took me a long time to kind of figure out how to work with Akka. And this is the one thing that I could like give to you that took me years of writing actor code to figure out. It's definitely that actors should be given instructions. They're not like dumb data stores. You blend together data and logic. And this is true of OO as well. And it's like a common sort of anti-pattern to see like these anemic domain models, right? These things, they just have data, they don't have any logic. That's what Fowler calls it. And it's really cool because if you listen to Alan Kay, who came up with the whole idea of object-oriented programming, he talks about message passing, and he talks about how you should tell instructions to actors that have data and logic together, and they should act like what we've been talking about with actors. They take an instruction, they do something with it. Alan Kay said, I made up the term object-oriented, and I can tell you I did not have C++ in mind. Because he was talking about message passing, and the way that OO has sort of progressed, I don't think he feels proud of his baby. So how do you do it then? If you're not giving a message and getting something back, then like how do you get real work done? And I think that the answer to this very often will be you make a temporary actor for the lifecycle of a request, because that actor can know exactly, it doesn't have to keep all the state about all these things going on. It can know just about its own context and expect a certain number of messages to come to it. So we can, if we need to get bank account info for the check-ins account, you can make a temporary actor that expects to get the account information from like some service, a database, and send a request to the service that will like forward the message. Say, hey, send, like when you get this data, send it back to this guy here. Send it back to this temporary actor, and he'll fulfill the request. He'll send the information to the user or whatever. So if we create a temporary actor, he knows he's going to get exactly one message from this account service, or he's not going to get any. He's going to time out and say, hey, we didn't get, like we got an error. We're going to have to retry that or whatever. So we can create a temporary actor. He knows about his like context. He knows that he's going to get one message, and he can like deal with any error situations accordingly. And that way, you're never like invoking things, like getting stuff back and working on it. You're just you're just telling things. You're just telling actors. You're just saying, hey, send a message to this guy when you're done. You can pass the context inside messages that actors need to do the work. And then, so your question earlier about consolidating data from multiple sources. So like if we have a chef who's making, like one guy's grilling the steak, one guy's making the salad, one guy's making the French fries or whatever, how do we sort of put that all together? I think a bank, you can think about getting your bank account screen online, like how do we see the checking, savings, and credit card information all at once? I like to refer to Jamie Allen's work from LifeEnd. He wrote a book called Effective Akka. It's really short. It's like 60 pages from O'Reilly. It had one piece in it that really caught my eye that I think is like it's the sort of awesome. It's a great heuristic. It's a perfect example of the tell, don't ask approach, and he calls them extra and cameo pattern. So basically, he just talks about the same thing, like spawning a temporary actor, having it contain context about the response, and dealing with any scenarios that come up along the way. Because he knows it. Yeah, I'll show you here. So again, the same thing. Like if we get somebody requesting their bank account information, we have this HTTP service. It'll make a temporary actor and send a request to savings, checkings, and credit accounts or whatever, and say, hey, give this guy back the information. He's going to have this temporary actor is going to expect in 5 seconds to receive the three responses. If he doesn't get them, then he has all of the context he needs to log the timeout information, for example. But yeah, so it's the same thing more or less, right? The Jamie Allen calls extra an anonymous actor, so you don't have to name the actor's class. You just go, okay, this new actor, okay, here's his behavior. And then that guy will expect to receive the responses. So it's kind of wordy sometimes if you're writing actor code that's like really idiomatic Akka. I tend to submit code reviews for my peers, and they're like, oh, like can we squish all this stuff together to make it more succinct? But the thing is that you get the safety by having the actors very flat and taking care of their one thing and telling other actors. So it's a lot more efficient than ask. So the ask pattern, where you give a message and you get a response in the future, that creates an extra actor and a promise/future every time you invoke it. So it's heavyweight. It's like if you're doing that thousands of times a second, it will eat memory because you're creating all these extra actors. You can condense that into like one time actor here, right? So if you have 3 asks to get the data, you have 3 temporary actors the actor will create under the hood. If you make just one, then there's like 0 futures and one extra actor. Okay, cool. I have like a little bit on distributed computing. I just put at the end in case we can get here, but I'm probably not going to present this because I'm assuming you guys are getting tired. But maybe we'll just do some questions.
Yes.
Yeah. Okay, cool.
Imaginary scenario. I have a box, let's say, and the box can contain up to 1 million of balls.
Okay.
I want to fill that box one more at a time. But because it's so big, so that I need several actors to fill that box.
Okay, sure. So
sorry, but because the actor, they no share state. The robot that fill the box, they don't know each other. So then their job is they fill the box. So then how do they know that when to start filling the box?
Okay, so So let me just frame this, make sure I understand. So people are sending messages. Oh yeah, okay. So you're saying like people are sending messages to somebody to process, like fill a box. Two guys are trying to fill a box.
At 1 million, they have to stop.
At 1 million, that's stuff. So this is actually a really tough problem that you're describing. And I'm gonna change the context of that. Let's say you have a service that's processing like requests, right? And you have two other guys requesting that work get done. Let's say like translation or I don't know, like any sort of service and client relationship. How do you let the clients know that they aren't overwhelming the server, right? Like any client server model is going to have actually this exact problem. So it's a tough problem. How do you notify people that are sending requests to slow up? How do you notify them that they can take more? And there's a new sort of draft called reactive streams, which describes non-blocking back pressure. There's an Akka implementation of reactive streams. So this is the problem. Like resource consumption needs to be controlled such that a fast data source does not overwhelm the stream destination. Clients making requests should not be able to overwhelm that server, right? If he gets infinite messages and they like queue and queue and queue, response times will balloon because it will have to go through the whole queue to get any new messages, and eventually it will run out of memory and crash. In Akka, by default, mailboxes are unbound, so they can grow infinitely until the application runs out of memory. You can change that, but it's the most efficient way to operate. So this problem is there's the specification of reactive streams talks about like signaling demand. So if I can take more, I'll tell the service, the client, hey, you can send me more, and likewise a signal that they should slow up if I'm out of demand, if I can't take any more on. So it's a very difficult problem.
Is it a share state that we should avoid?
Yeah, no, you don't get share state. You send signals, you notify, hey, slow down, or hey, I have I have the ability to take on more. But there's no shared state. It's still messages, right? You tell the guy, you have that one box would periodically send messages like, hey, I'm now at 200,000, or you can send me more, or stop sending me stuff now.
In that scenario, can we also model the box as a actor?
Yeah, sure. Yeah,
right?
State.
Yeah. The guy is like who put the doors to the boxer, and the boxer just pick it. Right? And if it's a full, and through exception or whatever, I cannot pick more. Something like that, right?
So shared state means that you can't change things that other people have seen at the same time. You can still signal and say, hey, the box is at 200,000 full, right? So you can still signal like that. You can send a message and say, here's like at the time of you asking, here's my state. So the cranes could go, okay, like, where are we at now? Like the thing's loading the box. Could get information about that actually? But I think the better model, the box should fill itself. Because you don't want things, you want the behavior and the state together. So your problem disappears if the box is filling itself, because it knows about its current state, right?
In that case, the box is the actor itself.
Yeah,
right?
Yeah. Everything that contains state in the actor system. Actors are the primitive. Actors are the primitive in the actor model. Does that kind of answer your question? There's a really hard problem, the demand, supply and demand problems with supplying servers, so it's a problem. But for modeling it, I think you would want the actor, the box itself to be filling itself. I think if somebody's producing balls, I don't have to think about it a bit, but you could draw it out with kind modeling in different ways and see what makes sense. Yeah.
So is Akka something that is meant to address distributed transaction as well? Would that sit on top of GTA or some other
Are you talking about like data store?
Like two-phase, so that's,
Uh,
how you would handle that account issue.
Well, so the problem of so if you're trying to put the logic somewhere different than the data, like have the data in a database and have the thing that's doing decrementing somewhere else, then you have problems with locking, right? If you have systems like that. If you can, the thing is we're building the application ourselves, right? So you can model it however you want. If you put the decrementing of the bank account in the same place that has the balance of the account, then you don't have to lock or anything, right? You can say, take out $20 and then we'll send you back an okay or no. So there are good transactional elements of Akka, like it had an STM implementation for memory transaction locking, but I think that was dropped from Akka. So the actor model implementation is kind of a different paradigm, a different approach. But then the same problems will pop up. We'll still have like distributed transaction issues. Like we use Redis sometimes where we're working right now for like distributed locking mechanisms. You can do like set not exist. And it's strong and consistent. So there are still, you'll still find even with Akka there are problems with like distributed transactions. Unless you can put the data and the logic in the same place, and then it's suddenly pretty clear that when you tell the actor to do something, it doesn't have to worry about like coordinating all this stuff because the state and the logic are in the same place. Does that kind of answer your question? I know it's, you can like look up Akka and distributed transactions or like because you have a strongly consistent actor. You have an actor that it can safely store and mutate its own state. You could say like you could use an actor as a lock mechanism. So you could say, okay, can I get the lock? Right? You know, multiple people are saying, can I get the lock? Can I get the lock? Can I get the lock? That lock state is one place. So you can like give back a an expiring token or something like that that says, okay, you have the lock now, and then when you send me back something like the token again, I can say, okay, yeah, you still have the lock, if it's okay, then submit it, or there are hard problems, like distributed locking is a difficult problem. But like check out Redis, you can get ideas about how to do it with a strong, consistent store, in memory store. It's not hard to model those approaches in that as well. Yeah. Maybe.
Yeah, is there any token in the message?
So by default we use Java serialization, I think, but you can change the message serialization to serialization. I would highly recommend you pick Google protocol buffers for distributed RPC serialization of messages. Definitely Google protocol buffers is sweet. It's used all over the place at Google. It's the de facto way to move data around systems. There are some faster implementations. There's like protocol buffers is cool. If you use it as directed, like don't require fields, then it's safe across versions of the application. But you can serialize however you want. You could like use JSON if you want. You can use whatever serialization you want. You can write your own serialization.
But it's not standard anymore?
The standard?
Yeah.
For Akka?
Yeah, for message.
Well, so it's not what it does, right? Akka's not a message serialization protocol.
Yeah, but in that case, so you have after you have instead after that, or you have a message the general.
Oh, sorry. It's just a class. Like within an actor system, it's a class. Yeah, but you want to make it immutable. So final editing, immutable types. But yeah, case class in Scala, using Scala, right? That's immutable sets or whatever. You send them around. If you need to send it over the network, then Akka has some default serialization strategies. That will use the serialized message and send it to the one actor. Deserialize it again, but you have to like look at your use case and sort of dig into if that works for you, I guess.
Yeah, I have a very similar question about the robot spelling the box, but I want to ask it in the context of the very first example you gave, where you're incrementing like 100 from 0 to 100,000 using features.
Yeah.
And then the second example you showed us how you would do it using actors. But just my naive understanding, the way you showed it in actors feels more asynchronous. Like you're
Oh, sure.
yeah, and so
there's only one thread in the actor.
right. So if you wanted that, if you wanted to do that work of incrementing up to 100,000,
What do you
basically.
do for it? Well, that's
No, I'm thinking, well, if you wanted to run concurrently, like
oh,
how
so you can't though, right? If the solution for futures is to lock, to synchronize when you get the value and then update it again. So, you know what happens if you synchronize that piece of code, that I equals I plus 1, it becomes flat again. It's only one thread is ever in there, right? So it doesn't matter what else is on the application. That's like the meat of your logic, and it's whatever you're synchronizing, there's only going to be one thread there. So the solution ends up looking pretty similar if you don't want to lose writes in both cases. If you're using locking, there's only one thread in that block of code, and similarly in the actor, there's only one thread that's running through the actor. So,
and if you did want to distribute the work, you'd have to communicate it using messages back to.
if you want to distribute the work of
Like yeah, that's just a trivial example.
yeah, well, okay, so if you're talking about distributing work, if you want, so we have one actor and you're sending it messages, and let's say it's doing really heavy computation, like it's transcoding video or something, right? It's something pretty heavy. Obviously, if you have to do, like where I work, we have to transcode video into different renditions, like 640 by 480, 1080p, 4K or whatever. In that case, the way that you may distribute the work would be to have multiple actors, right? If it's something like incrementing reply, then actors behind a rotor, so then you can have them all plus 1, send it back, or do or like here's this video, can you like transcode it and send it back the video, so you can distribute the work behind a rotor. So to parallelize, you create a bunch of actors and put them in front of basically a load balancer that will share messages around the work. But it's actually more efficient than a load balancer as well, because in a local actor system, there's this special mailbox, special router that will share a mailbox, and much like Goodwin, it has like a work stealing strategy, so any free actors will pull from the queue, which is better than them all having their individual mailbox, because then all the actors are always busy too, as long as it's work to do. Does that make sense? Yeah. Yeah, okay, well that's, to parallelize, you add more actors. Yeah. You put them on your other.
What are your recommendations on unit testing?
Yeah. So Akka has test kit. You definitely should be unit testing. I use Scala. Like Scala test kit. If you need the mock stuff, then Akka test kit has test control. The test itself can be an implicit sender, so you can expect it to receive messages in response, for example. You can generally inject actors wherever needed in the test programs. They can expect messages. I don't like using mocking frameworks with Akka. We have problems with Scala mock and Scala test and test kit working nicely with one another. But certainly, like for testing the code, like if you take a code in the receive block and you pull it out of the receive block and put it in a method, then you're able to unit test the method without testing the actor. So generally, like if you're unit testing, the easiest way to unit test the actor is to actually not start up actors with some messages. If you want to test that last little bit, that's cool. But you want to test the stuff you're likely to get wrong with most high priority. So it's simpler to pull the logic that you're trying to test and put it in class or in the object and test the logic. So there's different layers of testing, right? There's like unit testing, integration testing, where you're testing actors together, test actors, But yeah, so I'd say like the tools that I personally use, and I in my book I show you the same throughout the book as well. It's kind of added TDD or DDD or it's critical to do because you have to maintain software. Now it's broken. You can't write software like that. So I'm like running tests, and that's yeah. And if you Google it, you can find a copy. I'm sure you can around or like but it would show like some examples. Or actually, like GitHub account will also have like the test templates for almost all the tools as well. So you can see there if you want to get some Akka projects with unit testing. It's sort of so you can check that out. Yeah, that would be like for learning Akka on my GitHub account. You'd see like all the examples like Untitled Mask and like extra cameo. There should be some examples showing how you might do the test. I'm sorry.
You actually answered my question while answering.
Okay, cool. Any other questions? Thanks for your patience. I said I would go an hour and a half, Sean, but I didn't warn you guys, so. Thank you.
Thanks so much, Jason.